Hi folks, our lesson for today is related to point membership classification in Open Cascade. One of the main questions in geometric modeling is whether a point belongs to a solid or not. If we are able to answer that question, then our geometric system is known to be complete. So for today I would propose to see how can we check if a random point belongs to a solid or happens to lie outside of a solid using Open Cascade. For that, as usual, we are going to do some programming, and here I would like to head over to this GitLab which we have for lessons. It's gitlab.com /ssv lessons, and here you can find lesson number 17. Lesson 17, PMC. PMC stands for Point Membership Classification. We will start immediately from Visual Studio. I will do some configurations using CMake as usual, but let's not discuss it again, because in one of the previous lessons we devoted quite a lot of time to CMake configuration and everything related to how you get started with Open Cascade and dependent projects in Visual Studio on Windows. So what do we have here? Here, as usual, we have this empty main function which initializes this viewer, and also I put some stuff right before main function. This is something we would need to measure performance. So basically we are using this OSD timer. OSD timer is a class of Open Cascade. OSD stands for operating system dependent. What I want to do is I want to load a brep file. I want to have a solid model here in my application, and then I want to sample the ambient or modeling space with like random distribution of points, and then for each point to know if a point belongs to the solid or not. So this is a question which you might often ask a geometric system for whatever reason. As I mentioned, it's sort of a basic question. So for that, we are supposed to kind of provide a file name with the solid geometry using the input argument for our executable, and this lesson 17's PMC is an executable. So here in debugging, I'm going to put a command argument, right? And now I'm going to check if my argc, which is a number of arguments for my main function, is more than 1. It means that something is passed. So I can take this file name from there as usual and use this brep tools and then read. Here I would need to have a shape, and I would need to pass a file name which comes as an argument, and also here I'm supposed to provide something to construct this shape. For some reason, Open Cascade would require you to have an instance of this brep builder, or BB as I name it here. And now I only have to include the missing stuff. So let's go ahead and include these brep tools. And I would also need to declare this shape as top-ODS shape. Alright. So if for whatever reason this read returns false, then I will just return error status. Alright, now we have our solid geometry, and we can also output it to the viewer, just to have something to start from. So as you can see, I have this viewer here with visual output stream like, and you can see that here in my project I have this viewer and viewer interactor, and we discussed it the other day, all these visualization facilities which you might want to plug into your application just in order to be able to visually debug stuff as you are doing it. So let's try to run it for the first time. Alright, now you can see that I have this solid geometry, and now I want to kind of sample the space somewhere near this geometry or inside geometry, and to check if every point if it belongs to the solid or not. Let's see how you can do that using Open Cascade. And down the road, we will also cover a few interesting aspects of a library usage, which are not related to PMC, but still are quite something you might want to know about the library. So I think that as long as we are doing these small exercises, we practice not only the main topic of an exercise, but also practice how to solve, some common problems, common issues using the library, touch different aspects of the library, try different things, discuss different questions as they show up. So here I want to have like a bounding box of my shape in order to sample not the whole infinite space, but only this bounding volume, like this stock volume around my shape. Because I need to have a limited domain in order to do this point membership test. And for that, let's create this BND box, which is a bounding box representation in 3D space in Open Cascade. I'll call it AABB, which stands for Axis Aligned Bounding Box. And now we have this brep BND lib add, and then we add there the shape and also AABB as an output argument. And here we have this flag saying if we want to use triangulation or not. So if we have triangulation in our shape, like our shape was visualized in shaded view, and this means that we have this triangulation, and this triangulation can be used to compute bounding box very efficiently in terms of performance, but in terms of accuracy it will be limited with the accuracy. It will depend on the accuracy of your triangulation. So let's use it here, because we are not, we do not need any, very tight and very accurate bounding box to do this sort of an experiment. Now from the bounding box, we can take the min corner, which is as you can see, it's a GPPNT for the bottom left corner of our bounding box. And in the same manner, we can also take this Pmax as a corner max. And here also I would like to switch from GPPNT to GPXYZ in order to be able to apply some arithmetic operations. So XYZ would allow me to do some arithmetics on my coordinates. So now I would like also to take the diagonal of my bounding box, and for that I'm going to just subtract Pmin from Pmax. And now I want to take the largest dimension or the smallest dimension, depending on how exactly I want to sample my domain, how exactly I want to sample my bounding box. So let's just take its three sides, like three projections to the main axis: dx, dy, and dz. And now I would like to take the minimum dimension of my bounding box, and this way to control the grain size. So for that I'm going to have this min dimension, and I'll just take the mean among these dim values, elements of the dim array. Since this min function accepts only 2 arguments, I'll have to use it in the nested manner. Alright, so we have this minimum dimension. Now we can also specify some there, like density, how many points we want to have. Let me have something like 20, and now I'll compute a step size which is going to be the double value. And now I can deduce how many points would I need to sample each dimension of the bounding box. So here what I would need to do, I would need to take the dimension of the bounding box like this, divided by the step size, and then also to do some rounding operations. So I experimented a bit with all this, and you can just repeat what I am doing if you want. And now we can prepare the list of points, which is going to be just the STL vector of x, y, z coordinates, grid points. And now I'm going to run this nested loop for I, j, and k counters. Like I have this n slice 0 plus I, and the same would go for the second dimension of my bounding box and the third dimension of my bounding box. Alright. Here in this nested loop I can compute the point. Like, how would I do this? I will declare another gpxyz, and what I will do, I will take this min corner of my bounding box. As you remember, it's this corner min, and then I compose a small shift inside the volume of the bounding box. So there we go. And finally, having this point, I can add it to the collection of all grid points. So it's just, you know, a linear list of plain list of my points. I do not care that much about these 3 dimensions anymore. I just have like a single vector for the points. Then push back and my point P. So I guess here we would have this grid of points, and in order to test that we haven't made any mistake, I would like also to visualize these points as long as we compose their coordinates. So for that I take my visual stream, and here I would like to pass this P, but this visual stream, it doesn't accept in this exercise any geometric entity, so that's why I would need to convert, like to construct on fly this topological primitive, which is going to be a vertex here. So let's go ahead and create this brep builder API make vertex P. There we go. Basically, it's not the best idea to add points one by one to something like visual stream, to do something like this, because it would really depend on how this streaming operator is implemented. If what you are doing is you are creating like an AIS object for each individual point, then it's going to take forever to compose this sort of a scene, because you have many points and you will have a large number of objects. So it's better that you like put them in a compound and visualize this single object on a scene. And there is basically like a trick in this viewer. If you look inside the implementation of this viewer here, you will find this streaming operator somewhere. It should be like operator. It's not here, maybe it's in the header file. Operator. So what you can see from here is that we are having these 2 overloaded versions of this operator. One is for topods shape and another is for polytriangulation. And here for this topods shape version, what it does, it invokes this add shape function, add shape method, and if you go inside it, you can see what I put here like a trick. If what we put here as an input argument is a vertex, then instead of adding this vertex immediately to the collection of shapes, which is going to be visualized, and for each element of this list we are going to create this AIS object, we are kind of composing this single compound of vertices. So at the end, when it comes to visualization, it will be just single compound which will be visualized actually. So it's not going to be like this huge amount of vertices. And that's pretty important, because otherwise you will not be able to see any result and you'll wait for hours maybe. So now let's see what we will have if we run this small application like this. You see that we have this grid of points. Some of the points lie inside our shape, some of our points lie outside the shape, And now we want to classify them and maybe to keep in the scene only those points which belong to the solid, which belong to the interior of our solid. So let's close it for now and see how can we classify a single point. So now we are going to do this point membership classification by Open Cascade. Alright, and here I would like also to do some time measurements using this magic macro which I mentioned in the beginning, this timer new, timer reset, timer go. So these are just convenience macro which I use all the time, but you can see that it's actually just this OSD timer which does all the job. So we'll have here this timer new, then timer go. Here we put our code, something useful goes here, and finally timer finish and timer cout result with some message, and the message here would be like PMC by Open Cascade. There we go. So there is a tool in Open Cascade which is named brep class 3D solid classifier, which is a tool to perform this PMC with point membership classification. So I'm going to create it like this. I would only need to include it, I guess. Yeah, there we go. And what we can see from here is that we are supposed either to call this load method and to pass our shape, or we can also pass the shape right away in the constructor. So this is the option which I would like to use. We have this shape somewhere, yeah, it's our solid geometry, so let's put it here. And now I'm going to iterate over my grid of points and ask for each point if it belongs to the solid or not. Now I do not care anymore about these 3 dimensions because I have this plain list of points. So let me just go and maybe use range iterator here. And for each point I can use this perform method. As you can see, it accepts this point. And I'm also supposed to pass here some tolerance because I do not really know which tolerance to use, although this tolerance has something to do with the accuracy, and like you will have this small margin from the solid boundary to the interior, where points would be considered as inner or outer points or points belonging to the boundary. This is kind of a useful parameter, but I would like just to pass here precision confusion for the sake of simplicity. So at least let's start from it, and once we are done with this perform method, we can ask what is the status, current status of this classification, where is this state method, and if we are in, then I can kind of maybe compose another collection of points. Or for simplicity, let's just comment out this initial diagnostic output and just put it here. So if we fall inside the solid, then I would like to output this vertex, this point as a vertex to my scene. So let's see how would it work if we put it like this. So as you can see, it's kind of taken a bit of time right now. It's not immediate anymore. Did I make any mistake, by the way? So we have this range iterator. We construct this solid classifier out of the loop. Then we perform our classification and we check if the status of classification is in, then we output our result. So maybe it was not the best idea to kind of put this vout statement here, but according to our trick, it should be also quite efficient. Alright, as you can see, among the points which we had initially, only those points which belong to the solid or to the boundary of the solid are visualized. So if I hide this whole shape here, I would expect to see only these points inside the solid. And let me also try to comment this thing out in order to see if it is this line which contributes a lot to this execution time, to this total execution time. So you can see, even if I comment this line out, it's still going to take a bit of time. And also, I mean, notice that I'm running it all in debug mode. So in debug mode, it has certain overhead, and I mean, if you compile this exercise in optimized mode, in release, it should normally be much faster, and probably we'll have to switch to the release mode instead. Alright, so it's definitely not this line to blame. And it kind of takes 45 seconds in debug mode. Alright, so let's try to switch to release, and the only change which I would need also to make here is to pass this file name as an argument also for the release mode. And since the presence of this line doesn't make any difference, I would like to keep it to have some visual feedback, and for now I will also disable this diagnostic in order to see all the points which lie inside the solid. This kind of a solid which we are currently testing out is sort of like a complex one, so maybe it's not, I mean, the more complicated your shape is, the more time it takes to do this PMC test. And you see that in the release mode, like in production mode, you can expect this kind of performance. And you see that all the points inside the volume are also dumped here. Alright, I would not say that this result is sort of impressive, because, you know, this is not extremely large number of points anyways. So people who kind of face this sort of performance issue, they start to look around for a different solution. How would you like test a point, if it's inside or outside a solid? And here I put this classify PT header file, which does like an alternative approach. It implements an alternative approach to point membership classification. What it does the same sort of a thing, but on meshes. Like, instead of using this boundary representation or analytical or precise geometry, you first switch to meshes, like you have this faceted representation of your geometry. Then you build a bounding volume hierarchy around it, and then you do this very fast filtering. Like, you have a point, you quickly identify which bounding box it belongs to, and then in this bounding box, which is basically quite small one, you do this precise test for triangulation. So I'm not going to comment a lot about the contents of this file, because as you can see, it's quite large. We have almost 800 lines of code in there, so you can just probably take it and use it as it is, or we can discuss it on the forum if you would like. So let's try to make use of it. You can see that instead of a solid, now this tool accepts like polytriangulation. So the first thing we would need to do, we would need to assemble this polytriangulation out of our solid body. So let's try to do that. I'm going to use this classify PT thingy here, which you have to include first, and I already have this include statement here. So I would run different timer. Actually, it's going to be the same timer, but I need to reset it first. And then I will also wrap it with this sort of decoration, and it will be PMC by meshes. Alright, so we have this classify PT here. It would be like class meshes maybe. And here I'm supposed to put this polytriangulation. So I need first to construct this polytriangulation. And to construct this triangulation, you would need to know in advance how many nodes and triangles you are going to have. So basically, because we have this diagnostic output here, these meshes would be built for us by visualization subsystem. So if I have this line not commented out, then I can expect that in my shape I already have some triangulation. But I would not like to rely on this fact because it's not, it would not work on a backend, it would not work without any front end, without any UI, without visualization. That's why it's maybe better to forcibly construct mesh here. And for that I'm going to use a mesher of the library, this brep mesh incremental mesh, right? Which is also internally used by the visualization subsystem, but here we are going to run it explicitly. Let me call it like this. And I'll pass here my shape. So here I am supposed to pass some parameters, or I can just pass here this linear deflection and let the mesher to figure out all the remaining parameters by itself. And here I would use some tolerance, like this small number here, which is presumably like a fraction of a millimeter. And this is actually one-liner, and once this constructor is done, I already have some meshes generated. So I would put it outside this time measurement block in order to be fair, because I want to first build these meshes and then to do this classification test and measure this classification test only.